Welcome to Lecture 12, in which we're going to explore further the implications of that very big idea we developed at the end of the previous lecture, the idea of conservation of mechanical energy. The idea that we can transform energy from potential energy to kinetic energy and back and forth, and in systems where only conservative forces act, where there's no friction, no dissipation from air resistance, fluid viscosity, things like that, the total mechanical energy, the sum of the kinetic energy and the potential energy will be conserved. Now, last time I had my beautiful yellow ball bouncing up and down and illustrating the interchanges of energy between spring potential energy, gravitational potential energy, and kinetic energy of the ball. Here's a slightly simpler system. It's a mass, a block mounted on a horizontal spring. Animation of it, the block is moving back and forth with a particularly characteristic motion that we're going to describe in great detail in Lecture 17. But the other thing that's going on here is I've plotted a graph, and on the vertical axis of the graph is energy, and on the horizontal axis of the graph are simply two places, one marked U for potential energy, one marked K for kinetic energy. And what you can see going on as the mass vibrates back and forth, exchanging energy between potential energy when it's all the way to one extreme, kinetic energy when it's moving rapidly through its middle position, potential energy when it's at its far extreme. You can see the bars on the graph changing height as they interchange kinetic and potential energy. But if you were to add up the heights of the bars at any given instant, they would always add up to the total energy, which would be equal to the potential energy when the spring is at one extreme or the other, and equal to the kinetic energy when the spring was right in the middle. And we'll be using graphs like that to look at how we deal with potential and kinetic energy and their interchanges in mechanical systems. Now, one of the biggest reasons for understanding conservation of energy, one of the most practical applications of it, is it allows us to shortcut the messy details of problems involving motion, problems that would be very difficult to do using Newton's second law. We've already seen that it's pretty straightforward to solve problems involving motion with constant acceleration. Once we understand Newton's second law, that means motion with constant forces. But forces aren't always constant. Even something as simple as the force of a spring, as we've seen, is not constant, because the more you stretch a spring, the greater the force, and so the more force it takes to keep stretching it, and so the spring did not have a constant force. And so an object subject to a spring is not going to move with constant acceleration, as you could see in that animation we looked at, or as you could see with that big yellow ball I was showing you last time. Well, if we can't solve those problems using Newton's second law easily, how do we solve them? Well, one way would be to use calculus, and then we could work out all the gory details of the motion, at least in some cases. But even that's not possible mathematically sometimes. But conservation of energy cuts through all that and allows us to solve complicated problems easily. Let me give you an example here, a quantitative example. Simple one, but quantitative. So here are two skiers. They're each starting out from rest, and they're going to ski down frictionless slopes, and they're going to drop through a vertical distance h. The skier at the top is on a perfectly smooth slope. It's got a constant slope to it. That skier is going to be accelerating downward with a constant acceleration. I didn't work out the details of that acceleration, by the way, but I will tell you the answer for it, which, if you'd like to work something out for amusement, if you consider this angle to be theta, the acceleration down the slope turns out to be g times the sine of theta. Since the sine of an angle is less than 1, or 1 at maximum, that's a way of sort of diluting gravity. So this skier, we could solve the problem. How fast is that skier going at the bottom? Because that would be a problem involving constant acceleration. The constant acceleration, the diluted gravity along that slope. We know how to do that one. Here's a very different looking problem in terms of the physics. This skier is on a slope whose angle changes. The skier is going to start out with a relatively small acceleration, go over this hump, the acceleration is going to increase, then the acceleration is going to decrease, then they're going to get to the bottom. How on earth are we to solve that problem? If we were to solve it using Newton's second law, we would have to calculate the acceleration at each point here, and it would be messy. That's what calculus might be able to do if we could describe this slope with a simple mathematical function. If we couldn't do that, we'd have to throw up our hands. Couldn't solve this problem using Newton's second law. Conservation of energy is going to cut through all those details and make these two problems be essentially the same. So let's start by taking the zero of potential energy at the bottom of the slope. We're allowed to set the zero of potential energy anywhere we like. Then the initial potential energy of either skier is U sub zero, again that's sub zero for initial, is mgh because they are starting out at height h. And the bottom is where the potential energy is assumed to be 0. So they're starting out h above the bottom. All that matters is the vertical distance. And that's, again, because the potential energy and the work only involve the vertical component of the force. So each one starts out with potential energy U sub 0, U naught equals mgh. The skiers start at rest, so their initial kinetic energies are K sub 0, K naught equals 0. So we know their total energy. Their total energy is K naught plus U naught. K naught was 0, U naught was mgh, so that's just mgh. At the bottom, U is 0. So at the bottom, if they have any energy, and they do because energy is conserved, their energy is all kinetic. It's a half mv squared. And what we're after is v. We want to know how fast they're going at the bottom. So all we have to do is write expressions for the total energy at 2 points, one where we know the total energy, and one where we don't know it, but involves some unknown that we'd like to find. So if we write the statement of conservation of energy, we say that their initial energy, which was mgh, is equal to their final energy, which is a half mv squared. Notice, as usual involving problems with gravity, the mass cancels, again, because all objects undergo the same gravitational acceleration. We solve that, and let's see how we do it. We cancel the m, we multiply by the 2, and we take the square root. And the v is 2gh, and it didn't matter which skier I was talking about. The answers are the same, regardless of how complicated that slope was. Even if there was a loop-the-loop, like we did in the last lecture on there, as long as there were no losses due to friction, the answer would be the same. They would reach the bottom with the same speed, the square root of 2gh. Energy conservation cuts through all the details, especially in the second case where the acceleration is continually changing and we really wouldn't know how to solve the problem. But conservation of energy gives us a shortcut to the answer. If we do the numbers here, let's take h being 5 meters, about 15 feet, g about 10 meters per second squared. They're going to be going about 10 meters a second at the bottom, and that's about 22 miles per hour. It's an unrealistic problem because friction and air resistance are not insignificant for a skier, but they give us an approximate sense of how they go, and they show us how powerful conservation of energy is. When only conservative forces act, we cut through all those difficulties. Let's do another example of conservation of energy. Let's take a look at this little setup I have on my track here. I've got my little car, and I've got a spring, and I'm going to pull the spring back, and I'm going to use the spring to launch the car. And I want to ask the following question. If I know the spring constant, and I know how far I've pulled the spring back, how high up the track is the car going to go? So I'll do this simple experiment, and the car rose to some particular height up the track. I want to be able to figure out what that height is. Well, again, this is a conservation of energy problem. So let's move on to look at that problem. Here we are, an idealized example of that problem. We've got some block, that was my car. We've got a spring. We've got some initial potential energy because we've compressed the spring, and that initial potential energy is the energy stored in a spring, which we found out last time was 1/2 times the spring constant K, the stiffness of the spring, times how far I've stretched it squared. And here's our ramp, and I want to ask how high up it gets. So what's the height h when the block has risen to its maximum height before it's going to start going back down again, or the car in the case of my track? It starts at rest, so its initial kinetic energy, K naught, is 0. Its total energy is K naught plus U naught, and that's just a half kx squared. I should mention I'm doing what I did last time and taking the 0 of gravitational potential energy at the bottom. So it doesn't have any gravitational potential energy at the start, but it does have spring potential energy, a half kx squared. So that is the initial total energy, and the total energy stays the same all the time, so that's the total energy at any other time, including when it's up there. Well, what's going on when it's up there? Initial state, U naught, a half kx squared, K naught, 0. What's happening in the final state? Here's our total energy. In the final state, the block is at rest. It's not compressing a spring. And so the only energy it has is gravitational potential energy, and we know that that's U equals mgh, the force of gravity times the height. The force being mg, the weight. So that's the final energy. So the final state is U is mgh, K is 0 because it's not moving in that final state, at least instantaneously. It's stopped moving, it's going to start right down again, but for an instant it's at rest. So all I need to do now is apply conservation of energy and equate the initial energy to the final energy And that's an equation in one unknown. The unknown is h. How high up the ramp does it get? I can solve by dividing by mg, and I'm going to get kx squared over 2mg for the height. That's how far up the ramp it will go. Now, I present problems like this to students, and often they do the problem this way. They say, well, okay, the spring is going to launch it, then it's going to be going with some speed v, and I'll figure out what that speed is. And then once I know what speed it's going at, I can figure out how high up it's going to get. Don't need to do that. Conservation of energy cuts through all those details. Conservation of energy takes an initial state and a final state, and it doesn't care about any intermediate state. You could do the problem by first calculating the speed with which it leaves the spring, knowing its kinetic energy, in other words, and then figuring out the height, but you don't need to. All you need to do is start at the beginning, end at the end, and conservation of energy cuts through all the details and gets you there. Let's take a look, though, at this graphically. So there's the initial state. I've got another one of these energy versus type of energy graphs like I had in that animation. And now I have three types of energy. I have kinetic energy on the left, spring kinetic energy, U spring, in the middle, and gravitational potential energy on the right. We start out with no kinetic energy because it's not moving. We start out with no gravitational energy because I defined U equals 0 at the bottom. All the energy is in the spring. At the end, same graph, no kinetic energy again, no spring energy because the spring is no longer stretched, and it's all gravitational potential energy. Same amount, block is the same height as it was at the beginning. That's the way we solved the problem. If you wanted to worry about the intermediate situation right in there, after the block has left the spring and before it started rising up the rising part of the slope, it's got some kinetic energy. It's a half mv squared. We could find out what v was by equating a half mv squared to the initial kinetic energy, initial potential energy, 1/2 kx squared. I'm not going to bother to do that. But the point is, we could easily have solved for the intermediate state and then use that to solve for the final state. But we didn't need to. We went right from the initial state to the final state because conservation of energy cuts through all those details for us. Let's see how much faith we really have in this conservation of energy principle. Let's do an experiment that, if we don't believe in conservation of energy, is going to put us at risk. Here I've got a little demonstration set up. It consists of a massive bowling ball hanging from the ceiling, and it can swing like a pendulum. In doing so, it gains gravitational potential energy, it loses potential energy, gains kinetic energy, goes back up to potential energy, and so on. And in principle, if we believe in conservation of energy and we start it from rest with a certain amount of gravitational potential energy, it can never have more energy than that, and so it can never rise to a height higher than where it started. So to see if we have faith, or rather if Tricia here has faith, I'm going to ask her to hold this ball right up to her nose. Now you'll notice that the back of her head is against the wall, so she has absolutely nowhere to go to get out of the way of this thing. So if conservation of energy were not true, her face would be at great risk. So Tricia, when I tell you to, I'm going to ask you to release the ball, but the important thing is not to give it a push, because we don't want it to have any initial kinetic energy. We want its energy to be entirely at this point potential. It will be converted to the kinetic energy of its swing. It will be converted back to potential energy, and then back it will come. Are you ready? Okay, release. There it goes. Kinetic, potential, whoa! Back. And there it is again. She hardly even flinched. She has faith in conservation of mechanical energy. There is no way that bowling ball could get higher than where it started, which was right at her nose, and so her face is spared. Thank you very much, Trish. Well, as our bowling ball was swinging back and forth, its potential energy was changing, and it was changing as a function of where it was. When it was near the extremes of its motion, its potential energy was higher. When it was down at the bottom, its potential energy was lower. And that's generally true for all sorts of systems, not just mechanical systems like bowling balls. Potential energy varies with position, and understanding the potential energy curve, the function of potential energy as a function of position, allows us to learn a lot about how a system is going to behave. Perhaps the paradigm example of a potential energy curve is the roller coaster, as I have here on this track. And I'd like to take a minute and explore the energetics of potential energy curves using the roller coaster as a paradigm. So here's an example, a picture of a roller coaster. On a roller coaster, we're talking about gravitational potential energy. U is mgh, weight mg times the height. And so height is a direct measure of potential energy. So the actual shape of the roller coaster becomes a potential energy curve. And I've marked 3 different heights here. And I want to comment on what happens depending on what the total energy of this roller coaster car is. So at the graph at the left, got a quicker picture of the roller coaster, a simpler picture. Now it's a potential energy curve. It's potential energy as a function of position along that track. And if the total energy were the level marked E1 there, then that roller coaster would be free to move anywhere along that track. It would have more energy than the maximum potential energy it could have, namely the potential energy at the left-hand edge at the highest point on the track. On the other hand, maybe its energy, total energy would be E2. That's the energy it would have if it started right at this point A on the track from rest, so it had no kinetic energy, and then it would be capable of moving down the track up over this hump, and it could get up as far as here, but no farther. It would be trapped between those 2 points. We call those turning points. And finally, if it had an even lower energy, E3, and it started out here, it would be stuck between points A and B, or if it had started out here, it would be stuck between points B and C, between here. Only if it had energy greater than any of these humps could it get all the way out to the end of the curve. So that's an example of a potential energy curve. And I've got the same thing happening over here with the roller coaster. Here I have a large hump at the end and a smaller hump in the middle. And if I start the car about here, it gets over that hump. It had enough energy, enough total energy, that it could get to the top of this and still have some energy to spare, which would be kinetic energy, and it would still keep moving. On the other hand, if I start it lower down, say about here, it now doesn't have enough energy to get over that second hump, and it's trapped in this so-called potential well between these 2 turning points. Now there's friction here. It's gradually losing energy to friction, but in the absence of friction, it would be free to move in that so-called potential well. We'll see how these ideas continue even when we get way into quantum mechanics and we start looking at how atoms and molecules behave. We'll talk about their potential energy curves also. And indeed, here's a potential energy curve, not for some mechanical system like a roller coaster, but of the 2 hydrogen atoms that make up a hydrogen molecule. And you can see in this potential energy curve, potential energy is a function of position. We happen to define potential energy to be 0 when the 2 atoms are extremely far apart. As they come together, there is a minimum in that potential energy curve, and that's the state where a natural H2 molecule will be. That will be the equilibrium state of a hydrogen molecule, the state of lowest possible potential energy. That's the state the molecule will get itself into. If you give the molecule a little agitation, at least in terms of classical physics, it will be free to move about. Its size may change a little bit, and that describes the vibrational energy of a hydrogen molecule. If I want to separate the 2 hydrogen atoms to make them now separated and make them no longer a molecule, I would have to move up that potential energy curve until I got to the zero of potential energy far at the right of the curve, which corresponds to the molecules, the atoms being essentially infinitely far apart. Okay, let's change gears a little bit. We've been talking about energy for a while. Let's now talk about energy and something related, namely power. Energy is something, as I indicated, it's a conserved substance in the universe. It's like matter. In fact, Einstein tells us they're interchangeable. It measures an amount of stuff. But you'll often hear people talking about power. And power measures the rate at which you do work, the rate at which you use energy, the rate at which you generate energy, the rate at which you transform energy. It's about rate. And it's a very, very common misconception to confuse energy and power. The media does it all the time. Don't do it. Let me give you some examples. So energy is an amount of stuff. There's kinetic energy, for example. There's potential energy. There's electrical energy. There's etc. Lots of different kinds of energy. Power is the rate of energy use, the rate of energy generation, etc. It's the rate of doing work, the rate of consuming energy, the rate of generating energy. They have different units. Energy measured in joules, as we've seen. It's also measured in calories. More about that in a minute. It's also measured in kilowatt hours. That's how you pay for energy on your electric bill. It's measured in British thermal units. If you're an engineer in the United States or a heating contractor, you work with British thermal units. It's measured in electron volts if you're a physicist or chemist. These are all different units of energy. They're measuring the same thing. They can be converted one to the other. It's also measured in barrels of oil equivalent. A barrel of oil equivalent is the equivalent of the energy contained in a barrel of oil. Those are energy units. Power units, you're also familiar with some of them. Watts. A watt is the fundamental SI unit of power, and a watt is defined as 1 joule per second. So if I do work at the rate of 1 joule per second, or I consume energy at the rate of 1 joule per second, that's equivalently 1 watt. A horsepower, another power unit you've heard of, used to measure the power of car engines, is equivalent to 746 watts. It used to come from horses. Now it's defined as 746 watts. 1,000,000 barrels of oil equivalent per day, that's a certain rate of using energy. That's power. If you're in the oil industry, you might talk about power in those terms. Humankind's energy consumption rate, the entire population of our planet is consuming energy at the rate of 16 terawatts. That's about 16 times 10 to the 12 watts is the rate at which we consume energy. And you might ask, well, is that per day or per year or what? No, it's a rate. It's round the clock. Humankind is consuming energy at the rate of 16 trillion joules every second. To get you thinking about this, figure out what's wrong with this statement, which I picked from a leading newspaper, which I will not name. The new power plant will produce 500 megawatts each hour. Or another one, which I picked from a solar installer I won't name. The solar panels are rated at 7 kilowatt hours. What's wrong with both those statements? Well, pause a minute and think about it. What's wrong is 500 megawatts is a rate, period. The time is built in. 500 megawatts means 500 million joules every second. The solar panels are rated at 7 kilowatt hours. That's meaningless. I have to know how long the sun is shining on them to know how much energy they're going to produce. What they're probably rated at is 7 kilowatts, meaning they will produce energy at the rate of 7,000 joules every second, 7 kilowatts. Don't confuse energy and power. Let me do a couple of examples where we're going to calculate power. I'm going to do one harder example first, and then one rather quick, easy example. So let's move over to the big screen here, and let's do a couple of examples involving power and energy. Here's the harder one, cycling. What's the minimum power you would need to apply? That is, the minimum rate at which you would have to do work, the minimum rate at which you would have to supply energy to bicycle up a 10% slope, and 10% happens to be 6 degrees, at 9 miles per hour, which happens to be about 4 meters per second. And you and your bicycle together happen to have a mass of 80 kilograms. So this is not a trivial physics problem, but it's one of the kinds of problems you can do coming out of this course. So we know that the work it takes to raise a mass m, a height h, is work equals mgh. Seen that many times. That's the work needed. But we're not asking about work. We're asking about power, the rate of doing work. So the rate of doing work is going to be power, P. It's going to be the rate at which we're raising things up in height. So it's going to be mg times the rate of change of height. Delta H, change in height, over delta T, the time involved in making that change. Delta H over delta T is the vertical speed, which I'll call V vertical. It's the rate at which the bicycle is going up vertically. It's not the rate at which it's moving along the road. It's the rate at which it's rising vertically, which is going to be less than its actual speed. So the power is mg times v vertical. Okay, let's continue the calculation. There we are. We know that now what the power is. It's mg times the vertical speed with which this bicycle is moving up the slope. Let's do a little trigonometry. Comes in handy occasionally. That's a 6-degree slope. The sine of 6 degrees happens to be about 1/10. I can show you why later when we talk about radians and trigonometry, but for now it's about 1/10. The vertical speed is therefore 1/10 of the speed along the slope, because here's our 4 meters per second. That's the hypotenuse of this triangle with the 6-degree angle. The sine of 6 degrees is 1/10, and so this vertical arrow is 1/10 the length of that one. That's 0.4 meters per second. So V vertical is 0.4 meters per second. We can do the numbers. P is mg times V vertical. 80 kilograms was the mass. G is 9.8 newtons per kilogram, 0.4 meters per second. That comes out 313 watts. That's about 300-watt light bulbs. And by the way, that is roughly 3 times the body's typical average power output. Not surprising, because to bicycle up a 6-degree slope, a 10% slope, at even a modest speed of 9 miles per hour is a difficult job. So you're putting out energy at the rate of 313 joules every second, and I haven't even counted friction or air resistance or anything like that. But that gives us a feel for the power output of our body. It might be measured in the hundreds of watts. Let's do another one. Let's talk about driving. And this one's going to be a kind of back-of-the-envelope, quick, simple calculation. A gallon of gasoline happens to contain about 40 kilowatt hours worth of energy. So I want to know, at what rate is your car consuming fuel energy? That's again a question about power. If you're driving at 60 miles an hour and you're getting 30 miles to the gallon. So at 30 miles to the gallon, you're using 2 gallons to go 60 miles because you're getting 30 miles to 1 gallon. You're going 60 miles per hour, so that means you're using 2 gallons every hour. There are 40 kilowatt hours in every gallon. So you're using energy, gasoline energy, at the rate of 80 kilowatt hours per hour. Now, a kilowatt hour is the amount of energy you use if you consume energy at the rate of 1 kilowatt and do so for an hour. So 80 kilowatt hours per hour is something much simpler. It's simply 80 kilowatts. You want to get mathematical about it. The kilowatt hour per hour, the hours simply cancel, and 80 kilowatt hours per hour is 80 kilowatts, and that's about a little over 100 horsepower. You may say, whoa, I've got a 300 horsepower car. Am I getting robbed? No, your car's engine, whatever its horsepower rating is, most of the time it's not putting out energy at that rate. So here's an example that shows, again, typical numbers, they make sense. 107 horsepower sounds a little bit small for most American cars anyway, but it's in the right ballpark for a car's power output. So that's the rate at which you're using fuel energy to drive your car under these conditions. By the way, very little of that energy is ending up actually moving the car. Most of it is being lost to heat and friction and so on. So that's a quick calculation for power when driving. I want to end with a brief discussion of another energy unit you're familiar with, and that's the calorie. Here's a food label. You look at any food label, it tells you how many calories there are in a serving. What on earth is a calorie? Well, a calorie is a measure of the energy content of that food. If you burned the food or metabolized it, how much energy could you extract? It's not a measure of fat. It's a measure of energy. The calorie on food labels is actually a kilocalorie, 1,000 calories, KCAL, or sometimes capital CAL. A kilocalorie is about 4,200 joules, about 4.2 kilojoules. A typical human diet is about 2,000 kilocalories per day. And if you work that out, divide 2,000 kilocalories, convert it to joules, divide by the number of seconds in a day, which happens to be 86,400, you will find you get about 100 watts. And that means that your body is consuming in your diet energy at the rate of about 100 watts, and that's where I got that figure of about 100 watts for the body's typical energy output. In fact, if I were to stand here in front of you and do some exercise, say some deep knee bends, and I were to calculate the rate at which I'm doing work when I do this, and calculate how much height I'm raising my body and what fraction of my mass is involved, I would come out with a number that's just about 100 watts for my typical average power output. So we've seen a lot now in this lecture about energy and power. Let me end with a quick summary here. Conservation of energy, as we've seen, provides a powerful shortcut for problem solving. We simply write that K plus U, kinetic plus potential energy, is constant for the situation we're dealing with, and we solve. And then we've dealt with energy and power. Energy being amount of stuff, its SI unit being the joule. Power being the rate of using, producing, or transforming that stuff. Its unit is the watt, equal to the joule per second. Please don't confuse the two. You'll be real smart about energy and power if you don't. Okay, if you don't like a lot of math, you're done. If you like a lot of math, let me give you a very interesting challenge that combines several recent lectures. And here's the challenge. I'd like you to consider that loop-the-loop track we worked with before. Remember, I launched the car from a certain height and it got all around the loop, and if I didn't launch it from a high enough height, it fell off the track. So I would like you to find an equation for the minimum starting height h in this picture that will permit the car to get all the way around the loop without falling off. And we're going to make the assumption that the loop has a radius capital R, that the gravitational acceleration is g, and that the car starts from rest. And your equation should depend on these quantities only. That's going to take you a while to work it out, so press pause or stop for a little while and come back and I'll give you the answer. Okay, here's the answer. The height from which you have to release it is 2.5 times r, 5/2 r. And you might say, why isn't it just 2r? Because after all, if it's 2r, I could certainly have enough energy to get up to twice the radius, that is the diameter of the loop. But nope, it's 5/2 r, 2.5 r, and I'll let you puzzle about why that is.